No, maybe so.
All right, good afternoon, everyone. Welcome to the second set of student seminar presentations, where today 3 of our volunteers have kindly agreed to share the very interesting and wonderful results of their ongoing research. Just a reminder that there is money up for grabs, both for the winners of the presentations, as well as a $500 travel bursary for any conferences that you wish to attend in the coming year. With that said, our first speaker for today is Abdelrahman Ahmed, who's supervised by Professor Abdelrahman, who's kindly agreed to join us today. And he'll be talking to us about comparisons between simulated downburst loads at the Windy Dome and design wind loads for end house. So Pat, please, the floor is yours.
So good afternoon, everyone. So my name is Abdelrahman Ahmed. I'm a PhD candidate under supervision of Professor Ashraf Al-Dawati. So today I'm going to present part of the test we have done at Wendy. So the outline of today's presentation, we have introduction, then the objective of the study, and then the entire test at Wendy and the finite element model. Then we have the results and conclusions. So for the introduction, the downburst is one of the wind events that is identified as a high intensity wind event. So it is defined as a jet of air that impinges on the ground suddenly, then moves horizontally everywhere, creating vortices. So in the literature, majority of the weather-related transmission line failures are due to the high intensity wind events. So to make you familiar with the transmission line components, so this is a tangent tower, which is the typical tower that is replicated along the line. So we have the tower itself, and then we have the conductors, which transmits electricity, and the conductors are attached to the tower with insulators, which are free to move, and then we have the ground wire. So the end tower is the end point of those conductors. So it is designed to resist tension forces of the conductors from one end. And usually the end towers are stronger towers. So they have a role in limiting the cascade failure that may happen to the towers along the line. So the objective of this study is to identify the response of the end tower to downburst loads, and compare between the effect of the downburst loads on end towers and the synoptic wind load defined in the ACCE 74. So for the test plan we have at Wendy, so Wendy have a hexagonal shape with a diameter of 25 meters. So we have 3 identical towers, towers A, B, and C. So tower A is the edge tower, represents an end tower, while tower B and C are tangent towers. Then we have a rigid frame, which represents the continuity of the line in the direction beyond the tower C. So the line is placed such that the downburst is perpendicular to the end tower, with a diameter of the downburst of 3.2 meters and jet velocity of 9 meters per second. Then we move the downburst with respect to the end tower for a radial distance between R over D between 0.7 and 1.3, with an increment of 0.1. So the tower itself is made of 3D printed plastic angles with a geometric scale of 1 to 65. So this tower has a scaled frequency similar to the prototype tower. So we can call it an aeroelastic model. So those are the remaining scaling factors for the other quantities. And also we are modeling the cables, the conductors using a cable, which represents the scaled mass of the conductors. But here we are distorting the diameter of the conductor, the scaled diameter of the conductor. So we are adding a foam bolus as shown here to compensate the reduction in the aerodynamic forces of those cables, of the scaled diameter of those cables. So the cables here is attached to the end tower using leaf springs to ensure the rigid continuity, the rigid connection of the cables to the end tower. For the tangent tower, we're also simulating the insulator using an aluminum rod that is free to move. And for the end frame, we're also using the leaf springs as a rigid connection. So this is an overview of the tested line at Windy. And for the instrumentation, we have different instrumentation. We have a load cell to measure the base shear of the end tower. We have strain gauges to measure the tension forces in the cables. We have accelerometers. We have a high definition camera to measure the displacement of the cable. But here we are focusing on the response of the end tower, which is the base shear of the end tower. So this is the simulation. You can see here there is a smoke. This smoke has nothing to do with the test. It's just a visualization to see what is happening. So the obtained base shear of the end tower is decomposed into mean, background, and resonant components using the method developed by an Audi 2017. So first we have the time history. We divide the time history into mean and fluctuating component using the moving average method, where the cutoff frequency equals to the shedding frequency of the vortices of the downburst. And then the fluctuating component is divided into a background and a resonant component by isolating or filtering the resonance frequency in this signal. So when we add the mean component to the background component, we obtain the quasi-static response of the tower. So here is the results of the test. We have the base shear in the transverse direction, which is the direction of the downburst. So we can see that the maximum base shear happens at R over D from 1 to 1.2. We are almost close. And for the longitudinal direction, the direction of the cables, so we have the maximum base shear happens at R over D equals to 1. So we can say that the most critical case for the end tower is R over D equals to 1. So now we are modeling the tested line at the scaled model with the finite element model. So we are modeling the exact size and material of the towers and the cables. And here we are replacing the edge frame with a pin supports. First, we are validating the finite element model using the data we have from the test. So we are validating the frequency of the tower and the cables with the free vibration test we done at 20. So here we are comparing the frequency for the tower for the transverse direction and the longitudinal direction for the first two modes. And we can see there is a good agreement between the finite element frequency and the measured frequency. The same we have done for the cable, and we got a difference of 4%. Then we apply the downburst load we have at 20. So we calculated the load using this equation. So we have rho as the air density, and V is the downburst velocity we measured at 20. And CD and AD is the drag area and drag coefficient defined with the ACCE for the tower and the cables. So we can see there is a good agreement in the longitudinal direction for the base shear of the end tower between the finite element model and the quasi-static base shear. But in the transverse direction, there is the finite element model has a higher base shear, which indicates that the drag coefficient for the tower defined in the C code is conservative. So now we are applying the synoptic wind loads defined in the ACCE. So we have two load cases. One is a wind load with a reference velocity of 40 meters per second in the prototype scale. And the second one is the combination of the wind loads with a reference velocity of 13 meters per second and an ice accumulation on the conductor of 19 millimeters. So the ice accumulation will affect the weight and the drag area of the conductor. So we are calculating here the loads in the full scale, and then we scaled the loads down to the scaled model using the scaling parameters I showed in the beginning. So here we are comparing the axial forces in 4 chord members in the end tower from the synoptic wind loads and the downburst loads. And we can see that the downburst loads produce higher compression and tension forces in the chord members of the end tower. So we can say that the design wind loads are not sufficient to design the end tower to sustain this downburst. So we reduced the downburst velocity gradually to obtain a downburst velocity that is equivalent to the synoptic wind loads until we obtain a velocity of 6.45 meters per second. So we can say that if this tower was designed using the synoptic wind load, the traditional load, It can sustain a downburst with a reference velocity of 6.45 meters per second. So for the conclusion, the most critical case for the end tower for the downburst is R over D equals to 1. And the drag coefficient for the tower used in the ACCE is conservative. And the design synoptic wind load is not sufficient to resist the tested downburst, but it can be used to resist downburst in the full scale model of a jet velocity of 52 meters per second. Thank you for your attention. That's all I have.
Questions from our audience? Yes.
I was wondering, how did you apply the drag force into your finite element model? You showed us the calculation, so you have one force. And then is it applied at the nodes in the front?
Applied on the nodes of the tower.
Okay, so and how did you distribute it to the nodes? Because you got it from the experiment, like the base shear, right? That's the force.
No, we are calculating the loads on the finite element model using the velocity we measured at 20. So we have the velocity measured at different points. Then we have the if we don't have the velocity at a certain point, we do the equation. Then we apply the equation that I showed, that half rho v squared. So we have the velocity at the certain point, and we have the drag area and the drag coefficient from the ACCE. We then distribute the base shear again to the tower. We are applying the measured velocity at 20.
Okay, so from windy, it's the velocity, and then
And then we calculate the loads. And then we compare the results from the finite element to the base shear we obtained at 20 to validate the model.
Other questions from audience? Okay, excellent job. Thank you. All right, our second speaker of the afternoon is Yunpeng, who is supervised by Professor Claire Robinson, and he'll be talking to us about developing a geospatial tool to locate septic systems and estimate septic-derived photophosphorus loads to tributaries. Please, the floor is yours.
Thank you for the introduction. Hello everyone, my name is Yunpeng, and today my topic is about the geospatial tool to locate septic system and estimate the septic-derived phosphorus load to the tributaries. So a little bit background. So eutrophication has been a really important problem in Ontario and has been caused of millions of economic loss. So it's very important for us to understand the sources of this, where this nutrition comes from. So those nutrients and effluent has been classified in two classes. One is the pond sources, one is non-pond sources. So for the pond sources, they are like from the wastewater treatment plant and the factories. And from non-pond sources, there's from the suburban development and street, etc. So one of the two most important source of the non-pond sources is the suburban development and rural homes. So for the rural homes, they typically use the septic system to treat their wastewater. So the typical on-site septic system contains two parts. One is the septic tank, one is the soil drainage field, where the effluents are retained or attenuated in that zone. And if either of the part is not functioning well, the effluent will directly reach to the tributaries and damage our natural water bodies. And it is estimated that about 20% of septic systems are underperforming in Ontario. So currently in Ontario, we don't have any inventory about septic system numbers and locations. So to address this gap, my objective is to first improve the geospatial tool to spatially locating the individual septic systems across the Ontario Lake Erie and Lake Simcoe basins. And secondly, my objective is to develop a geospatial tool to estimate the phosphorus flows to tributaries based on the physical and social economic factors. For example, the permeability or the setback distance from tributaries, or the average household income or the home age for those septic systems. And this project is funded by Ministry of Environment and Conservation Parks. So the first step, how can we identify the septic system? So we first identify the rural homes using the LiDAR, the light detection and ranging. You can see here is the raw LiDAR point cloud data, and we can retrieve all the features above ground by its elevation. You can see those are buildings and those are trees. So we can retrieve all the things above ground from the point cloud data. And then from the LiDAR data, we calculate two parameters. One is the statistical standard deviation, and the other one is the texture standard deviation, which is based on the co-occurrence matrix. And by using these two parameters, we can kind of distinguish the buildings and trees from the LiDAR data. And then additionally, we found another data source is the multispectral error image. And based on this data, we can calculate another parameter, which is NDVI, the normalized different vegetation index. So this variable is partly based on the NIR and the near infrared light. And since the light is very sensitive to green color, and we know in vegetation, so all vegetation, the leaves are green, it's because they have the chlorophyll A. So by this feature, we can actually identify the trees and the grass. You can see this is the colored map. These ones are like the dark green ones would be the trees, and this would be the grass, and all these gray ones would be the bare ground, and those white ones are the buildings or some concrete structures. And in the end, we use machine learning methods to kind of summarize all these parameters and try to classify different classes from what we captured. So this would be final classifications. You see the red ones are the buildings, and those dark blue ones are soil or grasses, and the yellow ones are road or some low concrete structures, and the light green and the blue ones are trees. So after we got the locations of buildings, so how can we apply this to the septic system? So we can refer to the clearance distance for the class 4 and class 5 sewage system coming from the Ontario Building Code. And so here is the clearance distance we follow, and we kind of draw a ring shape near each buildings, and we place a septic system at the centroid within this ring shape. So finally, we have this result. So these are all the density map. So this is the density map for a 3 basin. We found like about more than 132,000 septic system, and for Lake Simcoe Basin, we found about 28,000 of the septic system. So in addition to that, I developed online tools to identify the number of septic systems within the region, and also to estimate the phosphorus septic derived phosphorus load in the region. And also it can demonstrate the physical and social economic characteristics for septic system. And the online tool will be made to public in late 2024, but it is already open to the university. So you guys can find it on the ArcGIS Online, the organization page. You can find it there. So here are some screenshots. So, here's the map of the septic system, and we can identify the number of septic system, and also the worst case phosphorus load, which is calculated at the scenario where we assume every septic system falls and all the phosphorus won't have any attenuations. So which is not true, but yeah, that's why we need a statistic model to kind of have a refined number. And also here we have all the physical characteristics within the permeability and the tolerant area. We also have the socio-economic factors such as the household income, age, the consumption. And one cool thing is so I add 2 filters, and you can kind of zoom in to like the area look you are located in London, Ontario, and we can zoom into that we have side in Upper Thames River watershed. So we can zoom into this watershed and see all the numbers are dynamic, and we'll zoom in and out or pan to another area, the number is changing. And also, if you want to come into a smaller sub watershed, can also do that. So this London is here, and we reside in the Medway Creek subwatershed. I can also do that. And also the odd numbers are dynamic. So kind of a summary. So a new geospatial tool based on remote sensing method developed to identify the individual septic system locations. And on tool developed for the user to determine the septic system numbers and phosphorus load in the given region. And my next step is to apply the statistical model done by my colleague Ahmed, and to calculate the refined septic derived phosphorus load in the environmental. That's it.
It's nice to see that you're making it public for everyone. Yes. I think that these are always nice to have. Questions from our audience?
Yes, you mentioned you are using machine learning.
Yeah.
So what is the role of machine learning? Can you?
So I use the k-mean clustering to kind of calculate the like different classes. We have like lots of the numbers, and it's also because our data set is too large. It's for the whole like year business about 6 terabytes. So if we use the like supervised method, it would be take so long because we don't have like a workstation there. It's not a supercomputer. So we kind of like make a balance like the computing power and the efficiency. We use the k-mean clustering to kind of cluster all these classes, and then we manually select so which one is which, and we fit this to the class we want.
Other questions from the audience? I have one. The LiDAR data, are those public?
Yeah, those are public.
Oh, so it's just topography basically.
Yeah, that's it's called the DSM, DTM, the digital term model, and digital term model, digital surface model.
Do you know what the spatial resolution?
It's about 30 centimeters, but yeah, it's like the actual one is 30 centimeter.
Yeah.
But they kind of make the like a kind of what do they call it? A kind of deduction, like to reduce the file size. They kind of did some algorithm to kind of merge some like similar pixels. So the actual one will be like about 1.2 meter, but like the smallest one would be 30.
That's very high still.
Yeah, that makes my file like the database really large, like 6 terabytes.
I see.
Yeah,
Yeah, that's a lot.
yeah, that's a lot.
Okay, cool, excellent. Final questions from anyone? Okay, very good. Thank you very much. All right. Our third and final speaker of the afternoon is Ali Abasi, who is supervised by Professor Ayan Sadhu, and he'll be talking to us today about monitoring and control of masonry walls. Please, the floor is yours.
Hi everyone, I'm Ali, a PhD candidate in structural engineering. Today, this is a presentation of one objective of my PhD thesis, which is monitoring and control of LDH masonry walls. So in this presentation, we will have 3 chapters. Firstly, talking about motivational gaps. Second one is full-scale wall testing and the results. And finally, we will review the conclusions of the study. Let's talk about the motivation and gaps. As you know, masonry is one of the most cost-effective materials worldwide, and there are lots of international standards for designing masonry structures safely. And there's not any problem on that section. But the problem is during the critical age, which is 7 days after construction, we call masonry LDH masonry, which is vulnerable to lateral loads, such as wind-induced lateral loads, and which results in the failure of the walls and as a result, loss of materials and injury to workers. There is a solution for that. The solution is using temporary bracing, as you can see in this picture. And there are two main references and design codes for the designing temporary bracing, but both of them are American, based on the American design process and based on the American masonry materials. But there's not any Canadian guidelines for designing temporary bracing. The main reference for designing and construction of masonry in Canada is CSA A371. And it is mentioned in this code that masonry shall be braced during construction. And it refers to Annex B. In Annex B, it is mentioned and that this section is informative and it's not mandatory. Why? Because there's not lots of details in this section for the designers to design the temporary bracing safely. And there are limited research regarding the material properties for the design of temporary bracing. So in this situation, designers are rely on engineering judgment, not the detailed material properties and the design process, which result in over-design temporary bracing or under-design temporary bracing. For example, in 2021, in Windsor, one LEH masonry wall, after 2 days, I believe, failed, and the results in injury to workers. So the main body is full-scale wall testing, which is experimental assessment of the flexural tensile strengths of the masonry walls. In this study, we can consider two different boundary conditions. Firstly is freestanding walls or cantilever walls. We will call it FS walls in this presentation. And then simply supported wall or SS walls in this presentation, for example, non-load bearing partition or infill walls. To be able to simulate both of these boundary conditions, we designed a setup which includes a wooden frame here, and which can be placed at the behind of the masonry wall, and we hang two airbags between the wall and frame to be able to inflate the airbag to push the wall until failure of the wall. And we connect one pressure sensor to the airbag to monitor the pressure inside the airbag to be able to convert to the lateral load which was subjected to the wall during the test. We had 7 LVDT sensors to monitor the displacement, 1 high-speed camera for DIC analysis, and 2 data acquisition system or DAC system to record the data from LVDT and acoustic emission sensors. 4 acoustic emission sensors to be able to do the crack detection, but I will not talk in detail in this presentation because we are still working on the analysis of the AE data, and 1 pressure sensor, as I talked, we will record which will record the pressure inside the airbags. So generally, we conducted 30 full-scale wall testing for SS walls and 30 full-scale wall testing for SS walls. And the samples address all ages from 5 hours to 672 hours, which is 28 days after construction. And pre-bag S Portland dime mortar based on the CSA code have been used in this study. For the analysis methodology, as our masonry was hollow on Bayfoot's masonry, we should assume that section are not allowed to be cracked based on the design standards. And this equation shows the relationship between the maximum tensile force in the section based on the MF, which is the moment at the section, PF, axial force in the section, and SE and AE are the section modulus and effective cross-sectional area. For the video that we recorded by the high-speed camera that I talked about it, we recorded the video for DIC analysis or digital image correlation. But at this stage, I used just the point tracking data to modify the data recorded by LVDT, because we assumed that the wooden frame was self-standing and self-standing system, and there wasn't any deflection in the frame. So we should prove that. Based on the videos, we did the point tracking to find out the displacement happened in the frame to deduct that displacement from the data from for the LVDT data to ensure that those data are correct. and those are regarding just the displacement in the vault. So after modifying the data, we analyze the data, for example, for SS walls, the failure modes is shows in the right pictures, and all the time the crack happen at the base, sometime in other rows of the mortar, but we remove those data as an outlier. After that, we did interquartile range technique outlier analysis again to minimize the variation in the data. And in the left picture, you can see the pressure data and LVDT data for one of the tests. You can see the abrupt failure happen at this point, and there is not considerable displacement in the recorded by LVDT before the failure of the wall. So we can say that materials doesn't show any plastic behavior, at least in these tests. So we can analyze them based on the static behavior and simulate them for the finite element simulation for next step. And based on the data, we conducted regression analysis. This picture shows the results of regression analysis, regression model for FS wall testing. And after outlier analysis, we had at least 3 acceptable tests for each LDH and T for curing time. So, and R-square value for the regression model shown as a 0.97, which shows a good agreement between the experimental data and numerical model. For the SS wall testing, the failure modes shows here. Again, the crack happen at the middle, but sometime in other places of the wall. So we remove those data as an outlier. And again, we conducted interquartile range technique outlier analysis to minimize the variation in the data. Based on the regression analysis, which was conducted for the SS wall testing, the model is presented here, and R-squared value was 0.98, which was a good R-squared value, which shows a good agreement between the experimental and numerical model, experimental data and numerical model. And let's talk about the conclusions. For the conclusion part, based on the results, we can say that there is inconsiderable flexural tensile strengths in the masonry or LEH masonry walls. During the first 24 hours, which is less than 30%, even less than 25% of the full strength of the masonry, which is really, which makes the masonry vulnerable to the lateral load. And it's necessary to use the temporary bracing. And there's not any considerable difference between the FS and SS data, so we can use them interchangeably. And the test shows abrupt failure, and regression models have been developed for the designer to be able to predict the material properties for any curing time that they want to design. And in future work now, in fact, we are working on the finite element simulation with Abacus for the models to be able to predict and see the properties and behavior of the wall for other ages and curing time as well. And based on those models, we can develop the model for other materials, for other sides of the masonry, to be able to develop the guideline. For example, in that guideline, we can mention how much is the maximum height of the wall without any bracing, or how much should be the maximum distance between the bracing along the walls. And thank you so much. This project was supported by NSERC and CMDC, Canada Masonry Design Center. And thank you.
Do we have questions from our audience? Yes.
Thank you for the presentation. How do you judge up to how many tests you consider are still safe outliers to exclude? Because it seems like for any type of test, you still have results that don't agree with the other results.
You mean how much should we need to do the test for every test to be able to have a good and acceptable outlier analysis?
Yeah, because there are up to what, like how tolerant are you for you to exclude results if they're outliers?
Okay. In the outlier analysis, we had in fact 2 steps for the outlier analysis. Firstly, it was based on the failure mode. because most of the, maybe more than 90% of the tests, the failure happened at the base. So any data that shows any failure in other points, we remove that data as an outlier. In the second part, we use the interquartile range technique. In the interquartile range technique, it doesn't matter how much is the number of your tests. It will consider the mean value of the test. Then any test data which is more than 1.5 times the mean value and less than 1.5 times mean value, which will consider as an outlier and remove the data. No problem. Yeah.
So my understanding, are you doing full scale test?
Yes.
And you are testing the walls with the bracing system, right?
Not with the bracing system now. It's in next step.
So
Now,
just freestand wall?
yes, freestanding wall and simply supported wall, because we don't know the material behavior, at least now, during the time. So
I believe people have done those kind of tests before. If it's just testing an unreinforced masonry under lateral load.
we didn't see any, at least based on the considering the effects of the curing time during the time. Some tests.
The main things that you are doing during the curing time.
Yeah, exactly. For example, we did some tests just after 3 hours after construction, 10 hours, 16, 24, 72, and the effects.
So why, you said you have two systems, you have simply supported and freestand.
Yes.
So simply supported will represent what kind of scenario in reality?
Yeah, in the construction, sometimes when we start the construction from the base, we will have for example, some wall view around the place or something, it will be simply supported. But if we use, if we continue the construction based on the previous construction, or using the wall as an infill wall or another situation, it's possible to be simply supported as well, if we connect it to the next level of the roof or something.
Yeah, but usually you finish the wall and then you do the roof after you cure the concrete, so likely it's gonna be freestanding.
Yeah, I see what you mean. But at this section, because we didn't do the testing separately for SS walls, we use the same test for SS walls as well. So it was it's worse to continue the testing without any paying for new samples and doing all the stuff again.
So your next step that you're gonna test it with the bracing?
Yes, yeah, and probably doing the test in the wind tunnel as well, with the scaled samples to see what will be their exact behavior subjected to the wall, to the wind.
Wind tunnel, to put the wall in the wind tunnel and the ceiling, that's gonna be very challenging.
Yeah, probably, but I hear that they have some facility, outside facility. So maybe we can do it now here. Thank you.
Other questions from our audience? No, if not, well, thank you again. Thank you so much. For today, Professor Jin Wang has kindly agreed to judge all 3 student presentations for consistency. And before you go, Emily would like to announce that we have an exit eye clicker.
Yeah, there's an exit eye clicker, so can you please make sure it's just the exact same as the entry eye clicker? Just go into your app and join the session. And we'll keep it open for, about 10 minutes. You have everyone the chance.
Yeah. So once again, exit eye clicker. Your eye clicker on entry doesn't count if you don't also do an exit eye clicker. Okay? Thank you all. See you all next week.